Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on carboxylic acids and derivatives. So this is topic 33 for the CIE specification, so that's the Cambridge Internationals. So if you're studying the CIE specification, then this is the right place for you to be, to cover some of the main areas of carboxylic acids and obviously the derivatives such as acid, chlorides, esters, etc. There's a full range of videos for year 1 and year 2 chemistry, so it's not just topic 33, it's 1 right the way through to 37, available on Allery Chemistry YouTube channel. All I ask is you hit the subscribe button just to show your support for the project. That'll be absolutely fantastic. But also these slides here, these are actually PowerPoint slides that they are available to purchase if you wish to. So they're great for your revision notes and putting your file, and obviously supplement your other notes that you've got as well. You can print them out and obviously scribble all of them. The link for the my TES shop is in the description box below, so go and have a look at there and see what's around there. So let's make a start and let's look at carboxylic acids and derivatives. Let's see what all this is about. So you'll find that actually what CIE have done is they've kind of split very similar topics with year 1 and year 2. So obviously this is the year 2 version. So I'm assuming that you've seen the year 1 version or the year 1 video, or have studied it, or or have a bit of understanding of it, because I'm going to kind of pick up from there. What you'll find as well is there's a lot of overlap with the CIE topics. They kind of overlap other topics as well, because some of the concepts obviously interlink. And as the topics are broken down to look at particular areas of chemistry. So for example, this is looking at carboxylic acids and derivatives. So you probably look at some of these and think, hang on, I think I've seen that before, which is probably true. So don't be alarmed if you see some things where you think, okay, I think I've seen this in another topic, and I'll try and bridge it as much as I can, but obviously this is just how CIE work it. So let's start with the formation of esters first. So esters are obviously a derivative of carboxylic acids, and we call this esterification. Now you would have seen some of this in year 1, but if you react alcohols with carboxylic acids, or acid anhydrides, which are kind of another derivative of that, don't worry too much about them. It's just kind of for extra information. But these can be used to make esters, and they have the COO group on there. So an ester is produced when we react a carboxylic acid with an alcohol and a bit of sulfuric acid catalyst as well. So there's your carboxylic acid reacting with the alcohol, and that forms your ester. Try to color code it as well so you can see where everything goes, and you form water as well. Another one is obviously anhydrides. You might see these. They're very similar to carboxylic acids, to be honest. I wouldn't be too concerned about this. It's merely carboxylic acids that you need to be aware of. But just in case you see something like acid anhydride or acid chlorides, as we'll go into a lot more detail later on, these will react with alcohols as well to form a carboxylic acid and an ester. So basically both of these will form an ester. That's what we're trying to say here. Okay. So in terms of esters, we need to know how to name them, of course. Now, esters are actually named in 2 sections. So the first bit is named from the alcohol used, and the second bit is named from the carboxylic acid. So let's have a look for this example here. So this is where we use ethanol as an alcohol, and propanoic acid is the acid. And this is the ester that's actually been formed here. But it's actually made up of 2 different parts. So you've got the alcohol bit, which is that bit there. So this part of the ester is actually formed from the alcohol that we reacted with, and there's the alkyl group. And in this example, this is ethyl, because we've got 2 carbons in there. Okay, and when you're naming an ester, this is the bit that you name first, even though in the molecule it's obviously on the right hand side of the molecule, as you can see here, or the right hand side of this group. We actually name that bit first. The other bit has come from the carboxylic acid, so this bit here. And instead of, obviously normally that says oic acid at the end of the carboxylic acid, so in this case it would be propanoic acid, and we replace it with O8 instead. So for example, this would be propanoate, and is named second when we're naming an ester. So in this example, this one's going to be ethyl propanoate. Okay, so you kind of flip it round the other way around. So let's have a look at another one. So this is when we're reacting ethanol with 2-methyl propanoic acid. So the difference here is that we have a branched group hanging off the carboxylic acid part. So again, when we're naming esters with alkyl branches, we number from the carbons in the COC bit. So this is the COC bit. That's always carbon 1, okay, and then 2, 3, etc. This one is carbon 1, 2, etc. So you have two numbering chains here because obviously the carbon chain is broken at this point because you've got this oxygen in the middle. So this bit here is obviously formed from the alcohol, and this is ethyl. This bit is formed from the carboxylic acid. So in this example, it is 2-methyl propanoate because you've got methyl group on the second carbon, and it's prop because you've got 3 carbons, so it's propanoate. So the full name of this is ethyl 2-methyl propanoate. Okay, so hopefully you get that. So you're naming it backwards to an extent. So you name this bit first, which is always derived. Anything to the right of this group here is come from the alcohol. Obviously, this bit here has originally come from the carboxylic acid. Okay, so let's look at some of these reactions. So carboxylic acids can be reduced to alcohols, and they can also be reacted to form acyl chlorides as well. So you would have seen again some of this in year 1, but carboxylic acids, obviously they can be reduced. We can use a reducing agent, normally lithium aluminium hydride, so LiAlH4, and we use a dry ether solvent. So this is effectively going from a carboxylic acid, so here this is ethanoic acid, with a reducing agent. Remember, we can use the square bracket and H to symbolize a reducing agent. And then this is obviously going to use water. So it's obviously going to be dissolved in, we're going to add water to it basically. And this is going to be reduced through to a primary alcohol. In this case, it is ethanol. Also, we can use the same carboxylic acid and we can react it with phosphorus pentachloride, which is phosphorus 5 chloride, as you can see there, and we produce an acid chloride, as you can see on this side. So this is your acid chloride here, and then we form POCl3 and HCl. So this is a different product. So here we formed an alcohol, and here we formed an acid chloride, but both of them are starting with carboxylic acid. So you've got to be aware of both of these reactions and what they produce. So just be really aware of that. Okay, so some carboxylic acids, we can oxidize them further to produce carbon dioxide and water. Now, we only need to know about the methanoic acid and ethane dioic acid in this example. So methanoic acid, these can be oxidized further. We're using Fehling's solution or Tollens reagent. So this is because obviously methanoic acid doesn't have an alkyl group attached to it, so we can actually use it. So there's your methanoic acid, which is here. We're going to use an oxidizing agent using these reagents here, and we can produce water and carbon dioxide. And the other reaction we need to know is about dioic acids. So basically it's just a double carboxylic acid, so ethane dioic acid. Again, using an oxidizing agent, we produce carbon dioxide and water. So just be aware of these reactions here when we're reacting either a carboxylic acid or a dicarboxylic acid. In this case, both products are just water and carbon dioxide. Okay, so make sure you're aware of them reactions. Okay, so we're looking at carboxylic acids. That's the whole point of this topic and all of the reactions that you need to know about them. One of the other features of carboxylic acids, as it suggests in the name, is acids. Now, this is where we're going to look at relative acidity of acids. Now, the example wants you to know about the relative acidity of obviously carboxylic acids, and we're comparing that to phenols, which you will have seen in the previous topic. And then you will also need to know about, so phenols is topic 32 by the way, and alcohols as well. So we need to know about, all of them have an OH group attached to them, but we need to understand why one is more acidic than the other. So that's what we're going to look at: carboxylic acids, phenols, and alcohols. So we're going to start with carboxylic acids first, okay? And they're acidic because they can donate a proton. So remember, that's the definition for Bronsted-Lowry acid. It donates a proton, or proton donor. And when dissociation of the proton occurs, we have a carboxylate ion that is left behind. And now actually this is found to have CO bonds that are actually of equal length. And that's a bit weird, because if you look at this reaction here, you can see you've got ethanoic acid, okay, and this is the ethanoic acid here. Now it's this OH bond that is broken at this point, and then we're left with this ethanoate ion. Now the weird thing about it is you've actually got a double bond and a single bond, so you'd expect the bond lengths to be different, wouldn't you, because you've got a double and a single bond. But it has this unique, well, fairly unique ability, which actually suggests that the electrons that are left here are actually delocalized in with the O and the O. It's actually spread right across there, and it looks a little bit like this. And this is the only explanation we can give, actually, to the fact that actually the bond lengths here are about the same. So the only thing we can suggest is actually it has been delocalized. Now what this means is you're left with an ion that's actually fairly stable, if I'm honest. So there is a negative charge that's kind of in there as well as the negative charge is spread across. But because it's quite stable, it means that actually as an acid, it can kind of dissociate, produce the proton, but the proton can then come back, if it wants to come back, I suppose, and rejoin to form a carboxylic acid. This is not really that bothered about rejoining the proton, mainly because of the stability here. This delocalized system stabilizes the kind of the negative charge here, and actually because the resulting ion is stable, then the proton is actually left dissociated. So that's quite useful. Obviously the OH bond breaks as well because you have a bit of polarity there. So this is why carboxylic acids are fairly strong in comparison to phenols and alcohols, which we'll look at next. So phenols and alcohol, like I say, are less acidic. They donate the proton less readily. Okay, so we'll start with phenols first. So phenols, as you will have seen in the previous topic 32, they do ionize, and you're left with a negative charge on that oxygen. Now, what happens with phenols is the negative charge, or the kind of delocalized electron system here, is then kind of merged into this oxygen. So some of this charge here is partially stabilized through the benzene ring system, and hence, it can lose the proton quite readily. It's not quite as stable as the carboxylic acid because you still have quite a lot of negative charge, as you can see, on that oxygen there. So it's not quite completely delocalized in here. Unlike with the carboxylic acid, where the negative charge can be spread pretty much wholly across the end of that carboxylate ion, it's not quite as integrated in here. And what you're left with is still something with quite a large negative charge on there. Now that makes it quite attractive for this proton, if it wanted to kind of reform a bond here and actually form the phenol back again. And this is why the phenol is actually less acidic than the carboxylic acid. Now, if we go into alcohols, alcohols are less acidic again, and this is mainly because they don't have the ability to delocalize any of the electrons. So if you break the proton away from, or the hydrogen away from the OH group in an alcohol, then you're left with a negative charge on the oxygen, but that can't be delocalized anywhere at all. So the whole charge is pretty much localized onto the oxygen, and that means it's open for attack for the proton to actually rejoin again. And really, in reality, alcohols you can't really class them as acids, to be honest. They really don't dissociate well whatsoever, because they just don't have the ability to delocalize the charge that's left behind. So alcohols, as you can probably expect, are really not acidic at all. Okay, so hopefully you understand that bit. Obviously that's quite important. Now moving forward, you're now going to see a lot of reactions to do with acyl chlorides, or also known as acid chlorides. Now, this has kind of been dropped in various topics previously, and you might have seen this name before. But really, in this topic, it's the first time where you're really going to kind of sink your teeth into the various reactions of acid chlorides and the chemistry of acid chlorides. Now, these are aggressive chemicals, okay, so they are incredibly reactive, and we're going to look at the properties of these as well and some of the products that they produce. So acyl chlorides, also known as acid chlorides, these have the functional group COCl, okay, and it contains the acyl group. So acyl chlorides are named by finding the longest carbon chain, and then we just add oil chloride on the end of it. So when naming acid chlorides, the carbon on the acyl group is always carbon 1, so it's exactly the same as if it was a carboxylic acid, no difference there. And the acyl group will always be at the end of the molecule. You're not going to get the carboxylic acid group in the middle. It's always going to be a terminal group. So this one is going to be ethanoyl chloride because you've got 2 carbons, as you can see there, and you've got an acid chloride at the end. So this one, just to kind of make it as complicated as we can, again, the longest carbon chain here or the longest continuous carbon chain is 4, so it's going to be butanoyl chloride. There's your 4 there. But on the second carbon, because we always call this carbon 1, the second carbon, we've got a methyl group attached to it. So there it is, 2-methyl butanoyl chloride. And then on the third carbon and on the fourth carbon, so 3,4, we've got 2 hydroxy groups. So it's 3,4-dihydroxy-2-methyl butanoyl chloride. So that's the name of that substance there. So you see, we're just using the IUPAC nomenclature that you've seen in year 1 to name these molecules here, except obviously this is a different compound. This is acyl chlorides or acid chlorides. Okay, so these undergo a certain type, quite a unique type of mechanism or type of reaction. And actually, you've heard the word nucleophile before, so that's fine. We know what a nucleophile is. It's nucleus loving. So these are species which have a lone pair of electrons and they attack a delta positive carbon. But they undergo an addition-elimination reaction. Okay, so quite self-explanatory. So you're adding something, then eliminating something. So you've kind of got an intermediate step here. So acid chlorides, they're, like I say, they're really aggressive chemicals. They are really reactive with many other different chemicals. And the reason for that is they have such a strong delta positive on that carbon, and it is susceptible to attack from nucleophiles. So that strong delta positive exists because you have your oxygen and you have your chlorine atom there. And now both of these elements are incredibly electronegative, and it pulls the electrons away from the carbon in the middle, and it basically strips it of of any form of kind of localized electrons within the carbon. So for that reason, like I say, it's going to attack pretty readily. It's going to be react pretty readily. So in this example, we're going to look at the mechanism for ethanol. So it's alcohol reacting with propanoyl chloride. So here we've got our acid chloride here. We've put our polarities on the molecule: delta positive carbon, delta negative oxygen, delta negative chlorine. So the electrons have been ripped away from this carbon, delta positive there. This is prime for attack from a nucleophile, which in this case is your alcohol. So this is methanol, lone pair of electrons. And remember, the electrons, when we draw mechanisms, the curly arrows must go from where the electrons are going from and where they're going to. So the curly arrow is obviously going to go from here straight into that delta positive carbon there. Okay, there we are. So that's your first sign of attack. Okay, it's the first thing. So once it's done that, obviously this oxygen now is starting to form a bond with the carbon. Okay. So a lone pair of electrons from this double bond must then break, because this is the next weakest bond. So you break in a bit of the double bond here, and the electrons will jump from here onto the oxygen. So this is forming a bond with the carbon, and then that's breaking the bond to form an O-. And this is where you have an intermediate. Okay, so you've got the whole molecule here, the oxygen, which has a positive charge here now, and you've got a negative charge on the side there. So what we've done is we've added, this is the addition bit here, we've added the alcohol to this intermediate here. Now you can see this doesn't look very stable at all, does it? So we've got a bit of a rearrangement here to do. Okay, so the electrons that are on the oxygen here, these will jump to form a bond with the carbon. Okay, now you can see the carbon now will have too many bonds. Okay, so the electrons will actually jump from this bond and kick off the halogen that existed on there. Okay, so the halogen's kicked off, and this is because this is the next weakest bond. So these are the reasons why these electrons are being broken from this bond in particular, because the CCl bond is weaker than any other bond here. So that breaks. I hope you're following. So we are left with this. Okay, so we've got the double bond that's reformed. Okay, we still have this alcohol group here with the positive charge that still exists, and that's the chlorine that's just being eliminated, I suppose, from the molecule. So this is still not suitable. Okay, this still doesn't work. So what's going to happen here? Okay, is the chlorine that was removed actually starts to form a bond with the hydrogen. Okay, it's not going to go for this. There's not enough room here. So it's going to go for the hydrogen. And then the electrons in this bond will then jump to neutralize this positive oxygen in here. Okay, so that will try to neutralize that. And then what we have is finally we have our product being produced. And our product here is an ester, as you can see here. So you've got methyl propanoate, because you've got your 3 carbons there, and HCl is formed. So this mechanism is quite detailed. There's a lot going on. You've got to understand, though, it's a 2-step process. You've got to add the molecule first, then you've got to eliminate the chlorine atom. It's always the halogen that gets kicked out of this. And this will be the same for loads of other molecules. This mechanism is going to be the same, this addition-elimination reaction. Okay, so like I say, this can apply to other nucleophiles such as ammonia, water, and amines as well. We're going to look at them as well. Okay, so let's have a look at the hydrolysis of acyl chlorides. So acyl chlorides will react with water in a hydrolysis reaction. Obviously, we've seen them reacting with alcohols there, but they will actually react with water. So they will produce a carboxylic acid instead. So there's your acid chloride, ethanol chloride, reacting with water. It'll proceed via exactly the same mechanism as we've seen before, and you might be asked to write that as well. Except instead of forming an ester, it forms a carboxylic acid. So this is going to be ethanoic acid and HCl. Again, it's a vigorous reaction. You get white mist fumes of hydrogen chloride gas. Not great. Definitely one to do in the fume cupboard. Okay, you shouldn't be doing this anywhere else but the fume cupboard. You don't want to be breathing that in. Now, I've tried to colour code these just so you can see where the elements are. Obviously, this is the blue, this has come from the water, and so is that. So we've basically split the molecule using water to form carboxylic acid. Okay, so acyl chlorides, alkyl chlorides, and aryl chlorides. Okay, so these can be hydrolyzed via water, and we've seen one of them already with acid chlorides. But they can be hydrolyzed via water and hydroxide ions. And what you will be expected to do is to make a comparison between them and understand what's going on here. So we're going to start with acyl chlorides first, and we've just seen this reaction. Like I say, we've just seen this just before. We know that acyl chlorides react with water and they form your carboxylic acid and hydrogen chloride gas. It's a vigorous reaction, definitely one to be done in the fume cupboard. So if we take the same reaction, so we react in water, but we're going to just react it this time with an alkyl chloride, so a halogenoalkane, for example. This has got a weaker delta positive carbon, so there isn't that oxygen and chlorine ripping the electrons away from the carbon. You just have chlorine. And yes, okay, there's a polarity, but it's nowhere near as powerful as this. So you would probably expect that the reaction isn't great. So we can add a chloroalkane to water and we get no reaction. Aryl chlorides are the same. This is the most stable. So you'll remember from topic 32 when you've got a chlorine, so an aryl chloride, so this is chlorobenzene, for example, that actually the electrons from here kind of delocalize into this ring, the benzene ring. That makes it quite stable. It's not really very reactive at all, so you don't get any reaction. Okay, so let's have a look with hydroxide ions. Now we're going to use sodium hydroxide in this example. Again, this very powerful delta positive carbon in acyl chlorides means you get an incredibly rapid reaction. You form a salt, so this is sodium ethanoate in this case, plus sodium chloride as well, because you've got the chlorine that comes off, and water. So there's definitely a reaction there. With this slightly weaker alkyl chloride group, we still get a reaction, but we need to heat it a little bit to get this reaction. So we form an alcohol here and sodium chloride. And then with aryl chlorides, again, you don't get any reaction because you've got this really stable benzene structure, this delocalized structure. So what we're looking for here is the examples really want you to try and explain what's going on here, okay, but also commenting on the strength of this delta positive carbon. And obviously it's strongest in the acyl chloride, slightly weaker in the alkyl chloride, and very weak in the aryl chloride. So it's just making these comparisons between these halogen based compounds. Okay, so acid chlorides or acyl chlorides, they react with phenol and ammonia and alcohol and primary amines. And in each of these reactions, as we've seen before, the chlorine is substituted either for an oxygen or a nitrogen that's been formed. Now, you need to know these reactions of acid chlorides with the various different chemicals here. So let's have a look at the reaction with phenol. Now, acid chlorides will react with phenol. There we are. Ethanol chloride will react with the phenol, and that will produce your phenyl ethanoate, so it's an ester, and hydrogen chloride gas. Again, a vigorous reaction, and I've tried to color code it so you can see where the elements are. Okay, reaction with ammonia, it produces amides. Okay, so we've got ethanol chloride reacting with ammonia, and this will produce your ethanamide or ethanamide, you can call it. Hydrogen chloride gas is produced. Again, it's a vigorous reaction. Okay, the mechanisms are always addition-elimination. Okay, there's no difference. So the mechanism that you've seen before is exactly the same for this. You might be expected to draw that mechanism, so be prepared to apply it. Okay, so reaction with alcohol produces esters. There we are, as we've seen before. So ethanol chloride plus your alcohol will form your ester. So this is methyl ethanoate and hydrogen chloride gas. Again, it's a vigorous reaction. Okay, and the reaction with primary amines produces N-substituted amides. It's a bit complicated, this one. So there's your ethanol chloride, and we've got your primary amine. And this is going to form your N-substituted amide, so N-methyl ethanamide. Now, I'm just going to kind of pause on this bit and just explain where this comes from. So instead here, you've got an N group here. Okay, you've got your NH group, which is at the bottom here. Now, normally, if it was an amide, this would be NH2, and you'd have 2 on there. But one of the hydrogens that was attached here has effectively been substituted for a methyl group, an aryl group. So in this case, it's going to be an alkyl group, sorry. So this is going to be CH3 in this case. So the N... So one of the hydrogens that was in N, it's an amide, okay, but one of the hydrogens that was attached to N has been substituted with an alkyl group. So that's why we say N, because it's a nitrogen, and the substituted bit is methyl, okay, because there's a methyl group attached there, and it's ethanamide, okay, so it's 2 eth, so it's 2 carbons, so it's eth, and it's amide because effectively you've got this carbonyl group here with an NH group there, but one of the hydrogens has been substituted for the CH3. So that's why we call it N-methyl ethanamide. If that was CH2, CH3 there, then that'll be N-ethyl ethanamide. Okay, so hopefully you kind of understand that. Now, you are expected to be able to know the addition-elimination mechanism for any one of these reactions here. Obviously, here I've just shown the equations down rather than go through each one, but cast your mind back to that mechanism that I've shown you before, and that's what you expected to know. Okay, and that's it. So that's everything you need to know for carboxylic acids and the derivatives for topic 33. Like I say, there is the full range of topics from 1 to 37 for CIE, all on the Allery Chemistry YouTube channel. Please hit the subscribe button just to show your support for this project. That'll be absolutely fantastic. In addition, like I say, these slides are available to purchase. They're bundled with the other topics as well from the test shop. Just click on the link in the description box and you can get a hold of them there. Great value for money. Print them out, put them in your file, write your notes next to them. Hopefully that should make your kind of revision that little bit easier. But that's it. Hope that helps. Bye bye.